Some engineers at NASA have designed a new kind of support beam that is able to be rolled up for launch and then unrolled in space. They are called deployable composite booms, and they're making it possible to pack some really big things into really small places.
In the last 10 years or so, with the advancements of thin-ply composites, it meant that we could use multidirectional fibers onto a laminate that would allow that structure to be ultra-thin. It becomes a deformable structure, which means it can be folded or rolled up around a spool, stored for launch, and then deployed to their operational configurations once in space.
They're lighter and stronger than what we originally used, say in like the Apollo era, where everything was made out of metal. So it was a lot heavier and it couldn't be rolled into a smaller structure.
Yeah, so that's two of them side by side. The weight of the boom itself is just 900 grams, so that's 2 pounds.
And the team will get to test their new rollable boom design on an upcoming solar sail mission.
ACS-3, or Advanced Composite Solar Cell System Technology Demonstration Mission, is a project to demonstrate in space that we can use the deployable composite boom technology that we're developing right now to deploy a solar cell system. This solar cell system would be about 9 meters on the side, so about a 80 square meter solar cell that would be deployed by 4 7-meter booms. Solar cells only use the power of the sun for propulsion. Basically, it uses light pressure. So as these photon particles impact the cell membrane, and the cell membrane being a highly reflective surface, it transfers that momentum back to the membrane and hence back to the spacecraft, pushing it in the opposite direction. The ACS-3 12U CubeSat will be launched on a rocket as a secondary payload. Once the system is deployed in space, it will open up the solar panels to generate power. Later on, it will deploy the solar cell by first deploying the booms, which reel out the solar cell membrane. And we'll have some cameras on the spacecraft that will image that process. And then we'll move on to a secondary objective, which is to demonstrate solar celling by orbit raising or lowering using solar radiation pressure. At the moment, we're developing 2 different sizes of booms. The smaller cross-section booms are for the ACS-3 Technology Demonstration Mission. These are 24 feet long or 7 meters long. And then we have a larger cross-section boom that is sized for up to 16.5 meter long applications. And that one has been sized for a scaled-up version that for now we're calling Hypercell. So the Hypercell system is about 6 times the size of the ACS-3 system. So it's about half the size of an Olympic pool.
And now the team has even bigger plans for this new technology.
The goal right now is to use these really long booms to build out more complex structures. We will target rollable straight ladders that could be used as ramps to offload equipment, straight trusses for lunar communication and observation towers, and to serve as high-stiffness beams for surface construction, and curved trusses to create dome structures. All of these could be assembled together like building blocks. We think that the composite booms will have a lot to say in how we get back to the moon. For the moon, we'll be targeting habitats for astronauts and hangars for equipment, as well as solar panels for power generation, also antennas for telecommunications. For example, since they're super compact, they could be add-on to rovers, so that when the rovers go into craters for exploration, you don't lose line of sight with your communication towers that would be outside, and it could enable communications of that rover back to the lunar lander or any other communication relays that might be outside of the crater.
Every day they're finding new uses for this technology, so be sure to check back with NASA for updates.